right, y'all. I would love for you to try to do this warm up on your own first before you watch this video. So if you have not attempted this warm up on your own first, please hit pause now and do the warm up with your group. Talk to each other about it, help each other with it. And I would say after about 5 to 10 minutes, you should go ahead and watch this video. All right, so this is a graphing problem, but it's also a modeling problem, which means that it's not just a graph without a context, but we actually have a context here. And this graph is going to be modeling a particular situation. In this situation, it is modeling the path of a satellite, and they give you R in thousands of miles with Earth at the pole. And then they go ahead and give you the equation for R. And so you are going to be expected to be able to graph one of these by hand using your knowledge of the unit circle. So R equals 4 over 4 plus 3 sine theta. I'm going to do a couple of them kind of off to the side. And we'll just work our way through it. So the first one is plugging in a 0. And so I need to think about, I'm actually going to make this is not theta, let's make it 0. The sign of 0 actually is just 0 because that point is 1 comma 0. And so the sign is 0. And so this just ends up going away, and I have 4 over 4, and so this is actually just 1. Okay, then I'm going to have 4 over 4 plus 3 sine pi over 6. And the sine of pi over 6 is a half. Okay, so it looks like this. On the test, we're going to give you one that's a little less obnoxious to do by hand, or when I say the test, I really mean the exam. So this is 4 divided by 5.5. And so you'll notice up here that I said you can use a calculator in radian mode to help with this. So I was actually assuming that you would just type these numbers into your calculator rather than evaluating them with the unit circle. And so if you do that, this is what you get. So there they are, all filled in. You'll notice that there's some patterns happening. And I wish that I would have put a 2 pi here. So you would plug 2 pi in and you would still get 1. Okay, so just a quick reminder on how to graph these. I'll graph a few of them and then I'll pause so that way it goes a little bit quicker. But for 0, 1, that means the angle is 0 and my radius is 1. So that would be that point right there. For pi over 6, I'm going to 7.727. So I'm really just kind of estimating here on these. It's not great. It's okay. This one is at like 0.5. Okay, it's something along these lines. Then notice that at pi, it's at 1 again, so it's like this. If I had drawn this a little bit better, we would have seen that this is a curve. Okay, so it wasn't great. That's still kind of lopsided. There we go. Okay, it's kind of like that. I've gotten all the way to pi. So 7 pi over 6 is here, and that's at 1.6. So I'm going to go a little bit past halfway. Then I'm at 2.13, which is going to be a little bit past the second ring. Then I'm at 2.85, which is even more past the second ring. And then I get all the way to 4. So at 3 pi over 2, we are at 4. 1, 2, 3. Oh, it looks like I'm at 3. Okay. I need to go all the way to 4. All right. And then it kind of repeats itself. So I'm back at 2.85, 2.13, 1.6. And then the reason why I added the 2 pi on there was so that you could see how this connects. It goes back to 1. All right, so if I connect all of those dots in a row, I end up getting this shape that looks kind of like an ellipse. Determine the minimum and maximum distances that the satellite is from Earth at any point. So it looks like Earth is right here, okay, at the pole. It looks like the closest it ever is away is 0.57, and the farthest away it ever is here at 4. And so remember, though, up here at the top, they said it was in tens of thousands of miles. So if I'm at 0.57 and it's in tens of thousands of miles, I'm going to move this decimal 4 times. So the minimum is 5,700 miles. That's at the top of the oval. And then the maximum is when it's at 4, but again, it's in tens of thousands of miles. So that means it's 40,000 miles, and that's the max, which happens to be at the bottom of our oval in this case. All right, suppose a second satellite passes through a point with rectangular coordinates 1.5, -3. Are the 2 satellites at risk of ever colliding at this point? Explain. So I kind of need to do some converting here. I need to, this currently, if it's rectangular coordinates, this is x, y. And so I need to figure out where this is in terms of r, theta. And for the moment, I can go up here and I could perhaps approximate the point. I'm going to do it in red. So 1.5 would be here, because that would be right in the middle of those 2. And then -3 would be here. All right, so this point right here. And so it appears on the graph that these do not actually ever collide. Today's lesson is going to help you with converting, and you could actually find the exact point. And we'll come back to this at the end.